let's talk a little more about force, work, and kinetic energy, and the relationships between them. So if we do work on a system, we know we are going to exert a force over some distance, delta x in this case. Now, if I put a force on this, its velocity, this block is going to get faster in that direction. And remember that kinetic energy is 1/2 mv squared. That means that the work you're doing by this force changes your kinetic energy. Now if we look at this, we're going to split work up into two parts, work done by conservative and non-conservative forces, and we're going to talk about the differences between them. We're going to start with a conservative force. Conservative is also path independent, meaning if gravity is working on this ball and the ball falls straight down, versus if I go, whoa, and follow this fun path, as long as you end up at the same point, the work done by a conservative force is the same. It's path independent. Gravity is a perfect example. So let's take a look at, well, what we can do with this. Here is our change in energy, and here's the work by conservative forces. Oh, so the force of gravity pulls down. That's where this little minus go. And when I say down, I mean in the negative y direction, because I set up my axis. And then we'll plug in our initial conditions. So we end up at 0. We started at y initial. And that goes to 0. And you get the same thing. So it all works out, and that's good. So we were able to put gravity in terms of conservative force. We're feeling pretty good about that. Let's move on. So what we can do is, well, let's rearrange this. I've got this work done by conservative forces, which I can cast as a change in potential energy. Oh, change in potential energy. Let's move that over here. And, what do we have here? Looky there. We have conservation of energy. Exactly. Except this work that we've been dealing with, that's the work done by non-conservative forces, something outside the system adding energy, which in this case is just going to be something outside the system is exerting a force over some distance. And remember, the directions matter, so you have to pay attention to these subscripts and your integration direction. Let's take a look at some simple machines. Starting out with this ramp, who does more work against gravity, A or B? Well, gravity pulls straight down, so all we care about is a vertical direction. Okay, I'm going to call this the y hat. They're both moving in the same y direction. Gravity points down, and they do the same amount of work. But why would people care about taking a ramp? Why doesn't this person just throw a grappling hook and then go, that's the grappling hook noise, and climb to the top? Interesting. Well, they do the same amount of work, but, who exerts a smaller force, who covers a larger distance? Well, we'll know that B goes this way for some s distance, and they exert some force along the ramp, because they're going up the ramp. Whereas A exerts some force straight up as they climb a rope or whatever. This distance S is larger, so B exerts a smaller force, whereas person A covers a smaller y distance, they exert a larger force. So even though the work's the same, the fact that you need a smaller force makes this scenario feel better, unless you like climbing ropes. So then, let's talk about simple machines and what they do, because it's not a work advantage, because you do the same work in either case. It's a force advantage. So the force exerted by A is proportional to the force exerted by B, but it's the distance at which you exert those forces that makes a difference. Longer distance, smaller force, bigger mechanical advantage. Because it feels like you're exerting less, well, you are exerting less force, but you have to work over a larger distance to compensate. Well, let's look at this. What if your system's rotating? Well, we know when we rotate, we are more concerned with this s direction. So instead of fx dx, our work's going to be the integral of fs ds. And ds we can write as this r d theta. Then we can pull out this little term right here, and we'll talk about that in a little bit. A couple lessons. So hold that thought for now. But let's look at something a little more familiar, which is a really neat result. So let's say we want to find the acceleration. What do we do? Well, to find acceleration, you go dE dx. So let's do that. It's 0 because it's isolated. The k term becomes ma, and this change in potential energy becomes F net. And you get, well, that's neat. Doesn't that look familiar? Well, this hopefully is helpful because our next lesson is going to be called Newtonian mechanics. Maybe that's a little hint. Now, very important, a force causes a mass to accelerate. Ma is not a force. If you see a mass accelerating, it's because a force acted on that mass to cause the acceleration. So Ma is not a force. It's what happens because of a force. We'll talk more on that later. Let's do a couple examples. Let's work this example. We've got a block on a ramp. It's going to experience a force of friction, and we're going to see what happens. Since I'm not worried about acceleration, I'm going to go ahead and use conservation of energy, which in this case, all I have are springs and gravity. Oh, and then work done by non-conservative. This is the new part that we're talking about right now. So if I look at this, I'm going to set up a coordinate system. I'm going to start with S pointing down the ramp. Then I'm going to say, oh, my spring's not compressed at the beginning. I'm at the ground at the end. So the only two things I have to worry about are my spring energy final and my gravitational potential energy at the beginning. And this is F delta S. We rearrange this. And what do we get? Oh, let's solve for the force of friction that we care about. Oh, wait, we need to figure out what that delta S is. So if this is Y, and I know Y, I know that S y equals S sine 30 degrees. In this case, I just rearrange this, and I get that S equals Y over sine 30 degrees. So when I finally plug in all of my numbers, I get F is equal to negative 9 newtons. Negative? Well, that makes sense because friction goes this way. This is the force of friction in the negative direction. And remember, that's all a minus is. It's just a negative. Let's talk about one final case. Let's say you've got this car stuck in the mud. You've got one pulley, and you've got to figure out where to put it. Do you put it on the tree, or do you put it on the car? Well, if we look at this case, we know the work done is going to be the same. If the person pulls 1 meter, the car moves 1 meter. So you move 1 meter of rope, 1 meter on the rope, and the car goes up the exact same distance. Well, if we know work equals integral of fx dx, we want to maximize the amount of rope we pull. But in this case, if the rope goes up 1 meter, this rope goes up 1 meter, the car goes up 1 meter. However, in this case, we move 2 meters of rope in the left-hand side. So what that means is this is how you want to hook that pulley up. And the reason why is because you're going to move more rope, which means less force to do the same amount of work. Car moves up 1 meter, you move 2 meters of rope. Hope that helps, and I will see you in class.